Hello. Hey, I have something here. What do you think? A little bit of olive oil and water. Um, there's a bug that got in there. I'm not sure how. Looks like it's a little less dense than water and a little more dense than olive oil. But I thought we'd just talk about this for a little bit. You know, what's happening here is, oil's less dense than water, but what's really happening is these water molecules have such a great attractive forces for each other. Water molecules, intermolecular forces are hydrogen bonding and London dispersion. And so what they do is just even if we shake this up, I don't want to shake it up. The water would just push all the oil away because the water molecules want to gather with themselves, and the oil just ends up at the top. Since it's less dense. The oil molecules, of course, they're really long hydrocarbons, maybe like 10, 11, 12 carbons. So that's just London dispersion forces. So we might talk about this every once in a while. Let's first talk about how is it possible that oxygen can be dissolved in water, because oxygen has to be dissolved in water for fish to survive. So let's look at how water is able to keep oxygen in solution. So let's think about a water molecule. A water molecule looks like this. Partially negative charge, okay? So then let's think about oxygen. Oxygen. So what we have to keep in mind is these valence electrons are free to move. So this oxygen molecule feels this negative charge, and the electrons in this oxygen molecule get repelled. And then, of course, they're getting repelled by this negative charge. And so this side becomes partially positive, and there's a little attractive force. Now, what we call that is dipole-induced dipole. Dipole-induced dipole. So this dipole here is inducing this nonpolar molecule to have a dipole. So water can dissolve everything. And if it's nonpolar, this is how water dissolves it. If we were to place some iodine, that's my dog Casey barking. If we throw in some iodine into this, I2, it would dissolve very well in the oil. It would sit in the bottom here, and eventually we would notice that the water's turning yellow because the iodine is dissolving because of this phenomenon, dipole-induced dipole. All right, let's go to, let's do this. I have some sea salt. Not sure why we have sea salt. My son Alex probably bought it. Sea salt, I think it has some magnesium besides sodium chloride. Those are both my dogs barking. I think my wife's home and my son Alex. So they get out of control when they hear the car running. Hey, let me just continue, okay? All right, so let's take some of this sea salt and sprinkle it into here, okay? Sprinkle it into here. We mix it up a little bit, and what would happen? Okay, so the question is some of the salt going to dissolve in the oil? And the answer is yes. So let's think about this first. So let's say we have a sodium chloride. So we have a sodium ion here, right? And then we have an oil molecule. Oil is just a really long hydrocarbon. Let me draw it like this, sorry. Okay, so here's an ion, non-polar molecule. And what will happen in this case, +1 charge, the electrons, the valence electrons in this molecule will be attracted Electrons will be attracted to this positive charge. This side will become partially positive. This side will become partially negative, and they'll attract each other. So there is such thing as salted oils, and this is how those oils can be salted. This intermolecular force is called ion. This ion is induced dipole. Okay? So ions can induce dipoles just like polar molecules can. All right. How about most of that sea salt went right to the water, dissolved in the water. Let's look at the intermolecular force occurring there. So if we have sodium chloride, you dump this sodium chloride into water, what will happen is the water molecules will surround the sodium ions. And notice I'm placing the hydrogen portion of the water molecule next to the chloride because hydrogen is partially positive. And what will happen is the water will be able to break this electrostatic attraction that these ions have. And we would then have a sodium ion that's engulfed in water molecules. This process is called solvation, by the way, and sometimes it's endothermic, sometimes it's exothermic, depending on this electrostatic attraction. Maybe we'll make a video of that sometime, knowing whether it's endo or exo. So when you dissolve salts, sometimes the solution gets cold, but sometimes it gets warm. So that's kind of interesting. This is called solvation. This process is called solvation. And what you have here is you have another intermolecular force. It's simply called ion-dipole. So you have an ion, and of course, water has a dipole. All right, so I think this is the rest of the intermolecular forces. So we're talking about dipole-induced dipole when a polar molecule dissolves or attracts a non-polar molecule. It induces it to have a charge. Ions can do the same thing. Ions can induce non-polar substances to have a charge. This attractive force is just ion-ion. That's an intermolecular force, ion-ion. And then we have here, in the case of ions being dissolved in water, we have what's called ion-dipole. We have an ion and a polar molecule that has a dipole, and away we go. So we have our oil and water. Think about what's dissolved in the oil. There's some salt in the oil. There's a lot of salt in the water. Sodium chloride has a huge KSP. Here's a thought. What would happen if we put some soap in this and shook it up? So I'll let you think about that, and hopefully you'll be successful with the intermolecular forces worksheets I give you. I think I got a little carried away, but I think you'll learn a lot by answering the questions. All right, see you.